Thank you, Barclay. A view as far as you can see. Unimaginable colors and shapes. Extreme dry and barren. Literally breathtaking. 66 huge radio dishes, and however large they are, they seem to disappear in the distance. About this, sorry. Yes. About this, about ALMA, I will tell you this afternoon. My impressions, more than facts. I have 40 minutes. This is a huge project, and I've chosen to concentrate on explaining my fascination and my impressions. And the facts, I will point you to the facts later. I had 3 jobs in 3 years in ALMA, and these three jobs I will use them to guide you through on a virtual tour through the project, because they are very well suited to explain what ALMA has gone through in those 3 years. And to make a little correction to what Barclay said, the observatory is there, it's finished, it's working, so it's a great success. My name is Rieks Jager. My background is project manager of large astronomical instrumentation, and this is an overview. At the top left, starting, that's a Beppo-Sachs satellite, wide field cameras in the X-ray region. At the left, the proud project manager presenting his 3 models, and at the right, an even more proud project manager with his 6-year-old daughter on his shoulder, watching the rocket just a few hours before it was launched. Great experience. Then I was involved in James Webb Space Telescope, the MIRI instrument, the mid-infrared instrument, so from X-rays to infrared. I was involved in one of the ALMA receivers, the Band 9 receivers that were built in Groningen in the Netherlands. Then ALMA, of course, that's the topic of my talk today. And now at this moment I'm working as a consortium project manager for one of the first instruments on the European Extremely Large Telescope, which will be hopefully ready in 10 years' time. So as a system integration manager, my first job, I spent about 1/3 of my time in Santiago de Chile, the capital of Chile. And here we find the headquarters of ALMA, the joint ALMA observatory, neighboring the ESO headquarters. First plans of ALMA, they came up at the end of the last century, when the three big partners, North America, East Asia, and Europe, got together and tried to join their 3 separate plans for submillimeter observatory into one big plan, so that there would be synergy there. The scientists were a big motor behind that, of course. That all worked out as planned. Total budget was about $1.5 billion, which is a lot of money, but as you can see later, it's actually nothing if you see what you get. Bit more than nothing. Operational cost $40 million, and by nature, because of the international collaboration, ALMA is a very international community. Here you see me in the center because I was chairing the team, a team meeting of my system integration team, and it's a mixture of test scientists and coordinators, and there were among the 7 or 8 test scientists, there were 8 nationalities, and if you ask me how is that, I think I can say I really enjoyed it. It's very inspiring. they were very motivated, and the differences are much smaller than the commonalities. It was a great pleasure. Every week, my colleagues and I flew 2 hours to the north, to Calama. It's the same distance as Amsterdam-Rome, on 8-6 shifts, 8 days on, 6 days off. And I can say that it's the best commuting that in my life. It's 6 hours door to door, and there was not one boring moment. So you travel across, along the Andes, very colorful, beautiful mountain range. You pass the Aconcagua mountain, the largest one of the Americas, almost 7,000 meters. You pass the Escondida copper mine. It's the biggest one in Chile and one of the biggest in the world. Not as deep as the one that Ronnie spoke about, 4.5 kilometers. This one is only 1 kilometer deep, open pit. It's a beautiful sight from above. After about almost 6 hours, you reach the Alma gate, where everyone has to pass that wants to visit Alma. You have to be pre-registered. There's a strict security system, of course. And then the last 700 meters up, we arrive at the operations support facility. It's the logistics center of Alma. It's a self-supporting desert island, where in the heydays, like 200, 300 people were living 24/7 together, living, working, sleeping, eating. Sorry about that. One back. On the right side here, there are the 3 vendor camps. The 3 partners each produce their own antennas. This is the American camp, this is the East Asian, the Japanese camp, and this is the European camp. They all have their own antennas. I come back to that later. This is the technical facility where all the offices and workshops are located. At the rear, there is the location where the antennas are integrated and tested. And over here, we have the recreational facility, the dormitories, the hotel facility, etc. And here you can see the road going up to, this is 3,000 meters. The level here is about 4,000 meters. And the Alma array operational site where all the antennas are located is behind that range at 5,000 meters. This is a view of the OSF as you see if you get off the bus. There's the dormitories and the antenna stations in the distance. Control room. The OSF is also the place where the telescopes are controlled from. And every once in a while, all the flags are raised. It's about 20 plus flags of all the countries involved. It's a real global collaboration. And they are only up when there's a special occasion, because if you leave them up in a month or so, they are disappeared because of the fierce UV radiation and the winds. So it's a special sight if you see this. So AIV, Assembly Integration Verification, was my main activity, was the main activity in the years that I was involved. That means that tons of special high-tech equipment from all over the globe arrives at the OSF, and we are putting them together like a rather complicated IKEA assembly kit. Sometimes with the same problems, with comparable problems that you might have, that we all know, I think. So as I said before, we can see here the 4 types of antennas, the North Americans, and it's easy to recognize from the outside because of the support structure of the secondary mirror, but there are more differences inside. And that's not, let's say, that's not the way you would like to design the project, but this is something that you get if you put 3 big parties together and collaborate in a beautiful collaboration but each party had the strong wish to spend, of course, a significant fraction of their money in their own industries. And so the antennas are different, but they function the same. The specifications are the same, the interfaces are the same. So all the equipment that will be integrated in the antennas fits in all the antennas. And if you ask the American ones, they say, well, we think that ours is really a bit better than the other ones. And the others, they say the same. And I can say that they're all good. They're all according to specs. And the differences are nice, but not essential. So don't believe them. Yeah, it's not, you don't have to read this all, but this shows the distribution of where all the subsystems come from. There, as I said, there are 3 big partners in the collaboration, and due to also the division of the work, the division of the expertises all over the world, there was well, this shows where all the stuff came from. Europe, East Asia, and North America. We will not go into details. If you want to know more, then I can tell you separately, or you can find it on the internet. System engineering here, for these, let's say, high-tech, close to the science equipment, has been very successful. There were multinational integrated product teams for all these equipments, where they coordinated the design, manufacturing, and testing. So it was, I would say, system engineering by the book, requirements, traceability, verification, interfaces, change control board, acceptance reviews. It was all in place and worked. This shows the first activity after we, that's the JAO, received the antennas from the antenna vendors that I just showed on the camp. This is the measuring and setting of the dish. The antenna vendors shall deliver the dishes with an accuracy of about 40 microns, which is already quite accurate. But what we need is 12 microns. And for that purpose, we have a holography tower where there's a millimeter wave transmitter on top. There is a holography receiver mounted at the secondary focus. And by measuring the pattern of the receiver here, this is a map before as we received the antenna, and this is a map after. That means that the guy here has a tool where he or she adjusts every separate sub-panel in this dish with so many microns that it will fit exactly the parabola that's needed. This picture is just a summary of, let's say, the equipment that was installed in each antenna. We have the receivers, we have the cryostat containing the receivers here. We have the back-end electronics, we have fiber optic wraps, and we have much more. And altogether, it takes 2 to 3 months before everything is integrated and tested. And my task when I started this first job was to speed up the AIV cycle from a few antennas, a few months per antenna to 2 antennas per month. And that was necessary because the project had to finish by the end of 2013, and otherwise it would have taken up to 2017 even. And we were successful there. It was a very good team. 2 to 3 months, 2 antennas per month means that we were working in parallel on 6 to 8 antennas, but sometimes we even had full house. There were 10 spots where we could work. So in this case, all 10 antenna locations were filled, and our teams were working in parallel on all these antennas. Okay, so after 1 year, AIV was on schedule. That was very good. And then I jumped to my second job, site construction manager, responsible for the power. It's the power station. Something completely different, but also very important. What I've seen in ALMA is that, as I just said, that system engineering and let's say on the high-tech stuff is very very successful, but on the low-tech stuff, it has gotten less attention. That means that that there were several problems with this power station. And when I kind of, let's say, volunteered after a year, said, well, let me try to do something here, then people said, you must be crazy. This is a headache thing. But I thought, well, it's not going very well, and it can only go better because one thing is for sure, this thing will work. So, and we did that. So I'm very happy that I was able to give my contribution. So why do we have a power station? Well, as I said, ALMA is the OSF and the other, the high side, is a desert island. That means that we are completely self-supporting. A few years ago, when everything was set up, it was investigated whether we could connect to the grid, which is the most logical thing to do, of course. But the nearest grid point is still more than 150 kilometers away. And ALMA uses only, let's say, a few megawatts. So it turned out that that was not sufficiently economic. So then the choice was made to become self-supporting. There were two issues with this power, with the power station in general. One is, and I will start with the first, but I will concentrate on the second. One is that the design and the scoping of the station was not optimal, and that's a system engineering related item. What was, let's say, not optimally done because of underestimating the amount of effort needed for system engineering, what was optimally done was keeping budgets. So when the order was placed for this machine, for these machines, the estimates for the power, the power needed had a certain level. And so now we have 3 of these machines, each capable of delivering 4 megawatts. And at that time it was fitting because we expected to have 7 megawatts, to need 7 megawatts. At the moment it's only 3 megawatts. So it's more than a factor of 2 oversized. And that is a pity, it's expensive. But there's not so much we can do at this moment. In the future, it will be possible. Another issue where I worked, and me and my team worked very hard on, that the quality of the deliveries was, let's say, not optimal. And that's partially also, that's also because these are commercial off-the-shelf machines in a way. There are thousands of these turbine systems everywhere over the world. But having one working at 3,000 meters in an extremely dry area is a different thing. So we had lots of problems getting this to work. Let me speed up a bit. So, I told you this will be a tour. So now we leave the OSF with an antenna on the special transporter. Here, it's a special machine. Antenna is has a mass of about 100 tons, very sensitive equipment. The transporter weighs about 140 tons, so altogether it's about 240, 250 tons going up the mountain. 27-kilometer long road, 2,000 meters up, 12 meters wide. And that brings me to another topic, which has also caused us some headaches. This is a special road. It's special because it needs to be very wide, and it's a mountain road, of course. It is not. There's no tarmac on it. It's a salt and soil stabilized road, which is very common in the north of Chile and in Peru, which is a good way to do it. But these roads, this type of roads, are vulnerable for water. That means that you have to take care that if there is rain, and there is rain, you can see there's snow here, that the water is not destroying the road. And as you can see here, that was not always successful. And in terms of system engineering, no, it's not so much system engineering. It's a matter of economy. All partners involved in ALMA had a certain budget, of course, and so this is a result of a not optimal balance between construction cost and operational cost. So here we see that if we would have spent a little bit more on a bit safer construction of the road, then we wouldn't have had these issues. But they were solved, of course, later on. So now, before we enter the AOS, the Array Observation Operational Site, I first want to mention the inauguration that we had in March 2013. At the center, you see the then President Piñera and the Director General of ESO and other directors joined with my team, our team, and this happened in March 2013. And at that moment, we were 80% ready for science, and this also signaled a very important priority change. Before that, AIV, construction, was main priority, and that made life kind of easy. After that, science was highest priority, which is of course very important, but made the remaining construction operations, construction activities more difficult. And this also signaled the start of my third job, head of ADE, ALMA Department of Engineering. But first, back to the tour. After a 5-hour ride, with about 5-6 kilometers per hour, we arrive at the AOS with our precious load, and the antenna is then transported to an antenna pad of where it has to be put down, and then it will be connected and made operational. So the first question you have, of course, and I will answer that question, is why are we here? Why at 5,000 meters in the Atacama Desert? Well, the answer is ALMA is meant to study the cold universe. So it's where planets are born, where solar systems are being born. Those features emit millimeter radiation. So it's very high frequency radio waves. And this is an example of just one example of a spectrum that will be measured, that is being measured. All these lines are signatures of sometimes very complicated molecules, and they show the composition of the gas clouds that are forming new stars and planets. And ALMA is tuned to observe in the atmospheric windows that allow these frequencies to pass, because these frequencies are very easily absorbed by water vapor in the atmosphere, so you have to go to a very high and dry place. And that is why this place in Chile was selected. So, how do we operate? No. Next one. Time to describe shortly how ALMA works. ALMA is a distributed telescope. That means that all these antennas together, we call them array elements, all these together form one big telescope. It's an interferometer, like there are more interferometers in the world, like the VLA, Westerbork, there are more. So this array can be changed from a compact array to a very extended array, and if it's extended, it functions as a zoom lens. So you can focus with very high accuracy to a small area on the sky. But sometimes you want to have a kind of a wide-angle lens, and then you put them all together. And that's very important, and that's the reason why on this plane we have a very extensive infrastructure, power, fibers, power and fibers mainly. So, and why 16 kilometers? The radiation that we receive from the sky is about 1,000 times longer in wavelengths than the optical wavelengths that we are sensitive, where our eyes are sensitive for. And what the astronomers want is they want in this wavelength range, in this sub-millimeter wavelength range, the same kind of resolution as we have in the optical. But if the wavelengths are 1,000 times longer, you need 1,000 times larger telescope. And that's why this 10 to 16 kilometer size has been chosen. That means that the resolution, the highest resolution, is better than with the biggest telescopes in the world at the moment, optical telescopes. So how is it organized? Well, we have a big building, a technical building at 5,000 meters. That's kind of the core at the high site, where the central equipment is located. It's kind of it hosts the heart of the observatory. You can envisage ALMA as a kind of an organism, where the eyes and the ears are the antennas. The brains is the correlator. That's a supercomputer, very specialized for specifically combining the signals from all these telescopes. We have I call it the nerves. Those are the fibers, and the spinal cord is the fiber optics patch panel. This is, in a way, it's familiar to the old-fashioned telephone systems, where usually a lady connected you to the party that you want to talk to, because the correlator can handle 64 antennas, 64 lines, but we have 190 positions where the antennas can be located. So that's why if you move an antenna from one place to another, you move the connection here. And these fiber optic connections are very specific as well, so you need trained staff to make these connections. 10 minutes. Okay, we switch from construction to operations. Now, first the central local oscillator, that's the heart. We need very precise timing at all the telescopes in order to do the correlation of these of the signals. So it looks like just a set of electronic boxes, but it contains a very strong laser, and it's a very sophisticated equipment. And that's all at 5,000 meters. So, operations. This shows that the climate at the site can be harsh, and this is nothing. It can be a real blizzard sometimes. So it means that there are very difficult working conditions. They can be very difficult. And it's always difficult because of the low oxygen contents of the air. We have about 55% of the oxygen that's at sea level. So if you need to work with great concentration, you need additional oxygen always. It's inaccessible during snowstorms or at night. So that requires very efficient maintenance. So if staff goes up to the high site, then you need to be sure that they work in an efficient way and in a safe way. So you need multi-expertise teams. You send up a car with an electronics guy and with a mechanics guy and with some other expertise that you need. And that was part of my duty as head of ADE, the ALMA Department of Engineering, to change, let's say, to rearrange the organization such that people, let's say, can work more efficient for maintenance. It's a different style, a different way of working, and a different mindset if you construct something or if you operate something. Well, this is one way to optimize the maintenance. We have two of these, let's say, kind of catering trucks. In this case, they cater the cryogenic front ends. Every year, a cryogenic front end has to be replaced. The cold head, the central cold unit has to be reworked. And you don't want to bring the whole antenna down, of course, just for this front end. And the front end is not a small thing. I showed you before. It's a real big thing. So what we do now is, I still say we. I only left 1 year ago. So what we do is we mount a new front end, cold front end in the truck. We drive it up. We exchange it here with the other front end, and the antenna is operational at the same evening. And then bring down the front end for refurbishment. One of the problems, and I mentioned the problems here, not because it was such a, let's say, well, it's everything that goes well is not news. So I mentioned the problems because it can teach us something. And in this case, what we found already quite early, but not easy to change, was that there was a certain lack of robustness of the system. These machines, these very high-tech machines, and the infrastructure is really well thought of, but it lacked, for example, remote monitoring and control. So although these receivers transmit, measure photons from tens of light years away, a million light years away, it was not possible to read out the power status of the antenna. So when we had a power glitch, we could not know which of the antennas was affected. It was all solved, but it's an example of where let's say solid system engineering, looking at the whole system, a high-level requirement is availability of the array, and what was insufficiently realized is that availability of the array influences also some basic features, not only the size of the dish and the efficiency, but also this what I just mentioned, remote control. But it was all solved, but it cost some time. So, what has been achieved? For the first time, We had such a large worldwide collaboration in astronomy, to have such distributed manufacturing, a large observatory to operate at 5,000 meters, a large interferometer at such high frequencies, all firsts. State-of-the-art technology in large quantities, 66 high-precision antennas, complete with sensitive cryogenic receivers. And beyond state-of-the-art technology in detectors, astronomers were really stunned by the first images that they got. And this, what I show here, is one of the first images. And everyone that sees it for the first time expects that it's an artist's impression. But it's not an artist's impression. It's a relatively nearby star. It's, I don't know exactly, 30, 40 light years. 1 million years old, very, very young star, relatively young. And this is actually a planetary system forming. So you can see a disk of matter, gas and dust. This is about the size of our solar system. So Pluto would be around here. Yeah, so this is a huge system. And where the dark areas are, the dark rings, are most likely areas where now new planets are forming. And this is absolutely unique picture. It was never seen before. So what made ALMA a success? A strong multinational, multicultural collegiality, a large dedication of staff, most staff, not everyone. Great science yield straight from the beginning. What I didn't mention is that even when we had only 16 antennas up, that was in 2011, September, we started with early science with a limited number of modes, observational modes, and with limited sensitivity, but already the whole system worked, from antennas to correlator, data analysis software, everything. So that was very stimulating for everyone to see that the system worked. And system engineering has been proven in many areas, as I showed, not all areas. What we see here is also a very nice result, I think. This is an Einstein ring. That means that it's a superposition of an ALMA image, that's the red, and a Hubble Space Telescope image, that's the blue. And the blue is a foreground galaxy at only 4 billion light years away. And it's exactly in line with another galaxy, which is 12 billion light years away. So it's really at the edge of the observable universe. And they're exactly aligned. And what you get is then gravitational effects, whereby the light from the faraway galaxy is amplified and distorted by the foreground galaxy. But there are ways to model this, the effects, and I don't have the results here now, but you can model this back. It is like a very bad lens, so it's very deformed, but you can model it back to the real form of the shape of the galaxy. So it's a very, very beautiful result. Okay, personal remarks. The problems that we saw were seldom really technically difficult. They were issues of will and politics and finances, etc. And it also shows where I think what we all know is that you can have solid system engineering techniques, but it only works if your let's say if your environment allows it to work. And the big connected to that is the largest challenge is to keep the shared set of goals and values, and to have open processes to resolve differences. When the going gets tough, the tough get going. And what we saw is at the end of the project, of the construction project, when the budget gets lower and tighter and more difficult, that it's more difficult to keep working as a team. We did it. We did it, but that was one of the big challenges. So for me, it was a once-in-a-lifetime experience. that's for sure. And I'm very proud that I have been part of this. What you see on the background is, by the way, it's a picture of almost exactly a year ago of Pluto and Charon on 2 days, 4 days. So this is Pluto. It's not a planet anymore, as you know. It's a dwarf planet. There are good reasons for that. And Charon is like our moon, around. How do you say that? Revolving. Revolving. And this, I show this picture because this measurement was done by ALMA in a wavelength range that fits with the temperature of Pluto. The temperature of Pluto is like 40 Kelvin, 230 degrees below 0 centigrade. And this picture allowed New Horizons to pinpoint even more secure the location of Pluto. So that helped making the location of Pluto much more precise. And this has nothing to do with ALMA, but I mean, this is 1 year later. 2 days ago, these stunning false color pictures, but the structure is as it is of Pluto and Charon. And I thought that was a nice way to end this talk. Thank you.